Good evening friends, welcome to ISRO marathon classes. Hope you all have come to know that the exam has been postponed from December 17 and the new dates will be published soon. We have an extra time for preparation now, so make good use of that. The subject for today is steel structures. So in this session we will be covering the questions from previous 5-year question papers of ISRO examination and also the most probable questions that we can expect for the coming examination. So without delay, let's start the session. Hope I am audible to all of you. Am I clear? Am I audible? You can reply in the chat box if there is any issue with the audio or video. Okay, so let's move on. Question number 1. Web crippling in a steel structure is on account of column action of web, failure of web under concentrated load, excessive bending moment, secondary bending moment. So the question is about web crippling. So let us see what exactly is web crippling. So we can see that there is an I section. We have a top flange, we have a bottom flange and a web in between. The localized buckling of the web is known as crippling. This portion has been deformed or buckled due to some load or some concentrated load. Similarly, this particular portion has also been deformed. So this localized deformation or buckling is exactly web crippling. So we should know that where does this occur? Where does the localized buckling of the web occurs? So this localized buckling of the web occurs at the point of application of concentrated load and at the point of support. So we should know the basics. That is, where exactly does this localized buckling occur? So it occurs at the point of application of concentrated load and at the point of supports. So coming back to the question, the correct option here is option B, the failure of web under concentrated load. As we have already seen, it occurs at the point of concentrated load or at the support. So in this question, the correct answer is option B. And please note that this question, exact same question, was asked previously in 2015 and 2019 also. Question number 2. So this question is about web buckling. So we have already seen how a crippling occurs and where it occurs. Now we have to see how a web buckling occurs. So web buckling occurs in a beam due to XC, direct tensile stress, bending tensile stress in the web, torsional shear stress in the web and compressive stress in the web. So what is exactly buckling? The sidewise bending is known as buckling and it occurs due to the excessive compressive stress in the web. That may be an axial compression or a diagonal compression or a longitudinal compression. So any compressive stress in excess can cause buckling in the web. So coming back to the question, so the correct answer will be the compressive stress in the web. Web buckling occurs due to excessive compressive stress in the web. So crippling and buckling are important. They have been asked multiple times for these examinations. So please note. Now coming to question number 3. The effective buckling length of a steel angle connected by double rivet system. This is a question from ISRO 2020. So let's see the standard values. So if we are using a discontinuous single angle section which is connected with one bolt or one rivet, the value is applicable for both bolt and rivet. So if it is connected using one bolt or rivet, the effective length is taken as 1L. Similarly, if a discontinuous single angle is connected with more than one bolt or more than one rivet or equivalent weld, the effective length should be taken as 0.85L. Now the question arises, what about the continuous angle section? If continuous single angles are used with one rivet or one bolt or more than one rivet or more than one, for both the cases, the effective length is taken as 0.7 to 1L. Okay. So note that also. So in the table it is about the discontinuous single angle section. So if we are using continuous single angle sections which are connected with either one rivet or more than one rivet, the effective length is taken as 0.7 to 1 mm. Okay. So here the question is, the angle section is connected by double rivets, that is more than one rivet. So the answer should be option B, that is 0.85 mm. Hope this is clear to everyone. Is that clear? Understood everyone? Can I move to the next question? Okay. Now, question number 4. It is about slenderness ratio. So, this is another important question we can expect for the ISRO examination. Slenderness ratio, what is slenderness ratio, the problems regarding this topic, or the theory, basic theory regarding this topic. So, here we are going to discuss the previous questions from this slenderness ratio and also the expected questions from this particular topic. So, let's move on to the problem. A 40 centimeter diameter circular column. So, it is mentioned that we have a circular column which is 4 meter long. The slenderness ratio of the column is, this is the problem. So, first of all, let us see what is actually slenderness ratio. Slenderness ratio is the ratio of effective length by least radius of gyration. Now, what is effective length? The length of the column or the length of the member which is effectively taking the load and which is deforming. That is known as effective length. And what about radius of gyration? It is the square root of I minimum by A. That is the least moment of inertia divided by the area of cross section. That will give you the least radius of gyration. So, here comes another question. What is the unit of slenderness ratio? So, as you can see that effective length may have the unit of meter or centimeter or millimeter. Similarly, the radius of gyration also has the unit in terms of meter or centimeter or millimeter. That means we have no unit. Slenderness ratio has no unit. It is a dimensionless factor. And what is the slenderness ratio used for? It shows the tendency of a member to fail. You should know that. So, basically we should learn what is that particular ratio and why is it used. So, if we know the slenderness ratio of a member, we should be able to say whether the tendency of the member to fail is less or high. So, if it is subjected to heavy loads or heavy loading conditions, definitely the slenderness ratio will be high. So, it shows the tendency of a member to fail, and it is the ratio of effective length by least radius of gyration. Now, let us solve the question. So, it is about a circular column which is 4 meter long, and we are asked to find out if the diameter is 40 centimeter, what is the slenderness ratio. So, let us solve. So, slenderness ratio is equal to effective length by least radius of gyration. So, let us find out the radius of gyration, which is equal to root of I minimum by A, that is moment of inertia by area of cross section. So, it is mentioned in the question that we have a circular cross section. So, what would be the moment of inertia? Pi d raised to 4 divided by 64, and the area would be pi d square by 4, and solving this we get d by 4. Cancelling 64, 4 etc. you get d square by 60, and taking the square root, the answer will be d by 4. And the diameter is given as 40 centimeter, therefore the value will be 10 centimeter. We get the R minimum as 10 centimeter. Now, the effective length is given as 4 meter. I am substituting in centimeter. So, 400 centimeter divided by 10 centimeter. So, the answer is 40. The slenderness ratio is 40. As many of you have given the questions given the answers in the chat box. It is answer is 40. Shibina, Binya. Yes, the answer is 40. So correct answer is option D, 40. Okay. So question number 5. So this is a very basic question. This has been asked in ISRO 2050. What is slenderness ratio? So this question has been asked many times in many examinations and is very important. What is slenderness ratio? Slenderness ratio of a compression member is. What would be the correct answer? Yes, Binya, Anida, yes, correct. Option C, effective length by least radius of gyration. Effective length by radius of gyration. Okay, so Vaishnav has said that the audio is not clear. Is there a problem with the audio? Can you hear me clearly? Am I audible? Is there a problem with the audio? Please reply. Can everyone hear me properly? Is there a problem with the sound? No issues. Okay. So Aishwarya and Vaishnav, please check your connection. Maybe there is a network issue. Otherwise, I think there are no issues with the sound. Okay, if there is any problem, please reply in the chat box. If anyone else has a sound problem, please reply. Okay. So we are moving on to the next question. So option C is the correct answer. Okay. Okay, please wait. Let me check if there is some problem and we will be back soon. Okay. So we will continue. If there is still a problem persisting, please tell us. Okay, now we will be discussing some probable questions that we can expect for the examination. Now let us move on to other details about slenderness ratio. So to solve this question, I would be explaining some more theory about the slenderness ratio. Now we have tension members, compression members, lacing bars, etc. Various steel members are there. And now we are going to study about the maximum slenderness ratio of different members. Okay. So coming to tension members, the maximum slenderness ratio of different tension members. So the easiest way to study this is, first you have to study the values on the right side. So concerning tension members, we have three values, 180, 350 and 400. After that, we have to study where to apply these values. So coming to the application of these values. So first of all, learn the values 180, 350, 400. So first case is a tension member in which reversal of direct stress occurs due to load other than wind or seismic force. So what are the loads other than wind or seismic force? That is dead load plus live load. So if we have a tension member with dead load and live load, the maximum slenderness ratio is 180. And the next case is a member normally acting as tie-in a roof truss or a bracing system subjected to a possible reversal of stresses resulting from the action of wind or earthquake force. That is, we have dead load, live load, wind load and earthquake load. So the combination is dead load, live load, wind load or earthquake load is acting on the member. The maximum slenderness ratio is 350 for a tie-in a roof truss or any other bracing system. And for all other tension members, the value is taken as 400. So for all other tension members means there may be vibration loads, there may be a rolling loads, there may be a cyclic load, there may be a combination of different loading conditions. So in that case, we can take the maximum as 400. So please note that if in a particular question we have said that a tie member in a roof truss then we have to go for 350. If it is said that just a tie member is in a structure which is subjected to so and so, then you can go for 400. So note the difference. If it is asked a tie member in a roof truss, you have to go for 350. And if it is said that just a tie member in a particular structure, you have to choose 400. So that is all about the tension members. Study the values 180, 350 and 400. Now coming to the compression members. So similarly, we will be studying the values first and then we will know where to apply that. The values are 180, 250 and 300. And where to apply these values? Members carrying compressive load resulting from dead and imposed load. That means we have a combination of dead load and live load. So if a compression member which is supporting a dead load and live load is given, the maximum slenderness ratio is 180. The same was applicable for a tension member with dead load and live load also. So it is easy to remember. Now coming to the second case, members subjected to compressive load resulting from wind or earthquake forces, provided the deformation of such members does not adversely affect the stress in any part of the structure. So we have a combination of dead load, live load and wind load or earthquake load is acting. So in that case, the maximum slenderness ratio is 250. And if it is a compression flange of a beam, so if we have an I-beam, we know that this is the compression flange and the bottom flange is known as the tension flange. So for a compression flange of a beam, we would take the value as 300. So I would just summarize the compression value, the slenderness ratio values. For tension members, it is 180, 350 and 400. And for compression members, it is 180, 250 and 300. Now let us come back to the question. So the question is like that. A steel member M has reversal of stress due to live load. That is, a member M is subjected to live load. And the member N has reversal of stress due to wind load. So wind load is acting on member N and live load is acting on member M. As per IS 800-2007, the maximum slenderness ratio permitted is. So what would be the answer? Can you tell me? One member is subjected to live load and the other member is subjected to wind load. So they are not asking about the values, the exact numerical values. They are just asking the comparison. So what would be the answer? Yes, Binya, Shibina. No other answers? Okay, they have answered correctly. The option A is the answer. The less for member M and than that of member N. That is correct because M has only live load and N has wind load. So as the load increases, naturally the slenderness ratio also increases. The tendency to fail also increases. So the answer is option A. Okay. So now let us solve a problem connected to the slenderness ratio values that we have just studied. Okay, so Aishwarya, Pranav and Vaishnav also have answered correctly. Answer is option A. Now let us see this problem. Two angles of 100 by 100 by 6 have been used as a tie member. So there is a tie member. The angle is welded on either side of the gusset and tag welded over its length. The maximum length of the member is. So the unknown quantity is the maximum length. And we are given that for ISA 100 by 100 by 6. ISA means Indian Standard Angles. Area is 2334 mm square and RXX is 30 mm. So we have to find the maximum length. So we know that slenderness ratio is effective length by least radius of gyration. And we are told that it is a tie member. So what is the slenderness ratio for a tie member? It is 400. If it is tie in a roof truss, the slenderness ratio is 350. For a simple tie member, it is 400. So how to solve this problem? So R is given as 30 mm. So slenderness ratio is equal to effective length by least radius of gyration, and we know that for a tie member the slenderness ratio is 400. So 400 is equal to effective length by R minimum, and the R minimum is given as 30 mm. So effective length is equal to 400 into 30. 12,000 millimeter, but our answer is given in meter. So it is 12 meter. So we get the answer as 12 meter. Yes, it is correct. Shibina, Ayana and Binya has answered correctly. The answer is option C, 12 meter. Option C, 12 meter. So is it clear to everyone? I hope it is clear. Is it okay? Can you follow me? Okay, if there is a problem, please reply in the chat box. I hope everyone can follow me. Yes. Okay, Binya. Thank you. Now, coming to question number 8. So, this is a very similar question from slenderness ratio. This has been asked multiple times in different examinations, including SSC also. So, according to IS 800 2007, what is the maximum permissible effective slenderness ratio for a tension member in which the reversal of direct stress occurs due to load other than wind or seismic force? So, we have already seen that other than wind or seismic force means it is dead load and live load. So, what would be the slenderness ratio? Please reply in the chat box. Yes, the slenderness ratio is 180. So, the correct answer is option C, 180. Yes. So, this topic is very, very important. We can expect a lot of questions from slenderness ratio. Now, moving to question number 9. So, this is from ISRO 2019 examination, and this question is about the buckling load. So, we are going to apply the slenderness ratio concepts and some other new concepts also into the buckling load phenomenon. Now, let us learn some basics about the buckling load. So, before learning about the buckling load, you should know the standard effective length conditions for the supports. So, basically we have three supports. Which are they? We have fixed supports, hinged supports and roller support. So, these are the standard supports that we have. So, what about the fixed support? For a fixed support, nothing is possible. There is no horizontal movement, no vertical movement and no rotation. And what about the hinged support? Rotation is possible in a hinged support, but there is no vertical movement and no horizontal movement. And about the roller support, rotation and horizontal movement is possible, but there is no vertical movement. So, you should have a basic idea of what is possible for different supports. And with this basic knowledge, let us see the effective length condition for these standard cases. So, coming to the case 1. If a column or a member is effectively held in position, which means there is no horizontal movement and no vertical movement. So, whenever you see the sentence like there is effectively held in position, then you have to guess that there is no horizontal movement and no vertical movement. And restrained against rotation at both ends. That means rotation is also not possible. So, what is the summary? We have a column or a member in which both the ends has no vertical movement, no horizontal movement and no rotation. What is that support? It is a fixed end support. So, if we have a both ends fixed condition, the theoretical value of effective length is 0.5 L and the recommended value of effective length is 0.65 L. And you have to see that if nothing is mentioned in the question, you have to go for recommended length. If it is mentioned that what is the theoretical value of effective length, then you can go for 0.5 L. So please note that if nothing is mentioned in the question, you have to choose the recommended value. So for both ends fixed condition, the theoretical value of effective length is 0.5 L, which can be written as L by 2, and the recommended value is 0.65 L. Similarly, coming to the next case, effectively held in position at both ends, which means at both the ends there is no horizontal movement and no vertical movement. Restrained against rotation at one end. So one end has no rotation also, but the other end has a rotation. We are not restraining rotation at one end. So what would be that support? If there is only rotation possible, that would be a hinge. So one end is fixed and the other end is hinged. The theoretical value is 0.7 L, which can be also be written as L by root 2, and the recommended value is 0.8 L. So you have to remember these values. Problems can be asked or theory can also be asked. So if both ends are fixed, the values are theoretical is 0.5 L and recommended is 0.65 L. And if one end is fixed and other end is hinged, the theoretical is 0.7 L or L by root 2 and recommended is 0.8 L. Now moving on to the next case. Effectively held in position at both ends. So both ends have no horizontal movement and no vertical movement, but not restrained against rotation. That means rotation is possible at both ends. So obviously the supports are hinged. So if it is both ends hinged condition, theoretical and recommended value is 1L. And the last case. So these are the 4 standard cases you have to remember for solving the buckling load. So effectively held in position and restrained against rotation at one end, but not held in position nor restrained against rotation at the other end. So that means one end is fixed and the other end is free. Then the theoretical and the recommended value is 2L. So these are the standard cases you should remember to solve the buckling load. Now coming to the Euler's buckling load. So the Euler's buckling load is given by the expression pi square EI by effective length square. So PCR means critical load, that is the expression. E is the modulus of elasticity of steel, I is the moment of inertia, and effective length should be taken as the theoretical value. We have already seen the theoretical value and recommended value, and for Euler's critical load condition we have to choose the theoretical value for every case. So the equation is pi square EI by effective length square. Now coming to the case 1, both ends are fixed. So we know that if both ends are fixed, the effective length, theoretical effective length is 0.5 L, which can be written as L by 2. So substituting L by 2 in this expression, we get 4 pi square EI by L square. We are substituting L by 2 the whole square here. So 4 pi square EI by L square. Now the next case. Both ends are hinged. So we know that if both ends are hinged, the theoretical effective length is equal to the original length itself. So pi square EI by L square. The case 3, one end fixed and other end hinged. So we know that the theoretical effective length will be 0.7 L, which is equal to L by root 2. So when we substitute L by root 2 in place of effective length, we get 2 pi square EI by L square. So you don't have to by heart these final expressions. You just have to know the effective length, both theoretical and recommended. But for Euler's critical load, we need to know about the theoretical value. And coming to the last case, one end fixed and other end free. And for that case, the effective length will be equal to 2L. And substituting 2L in terms of effective length, we get 4L square, that is pi square EI by 4L square. And you should also know the expression for Euler's critical stress, that is pi square E by lambda square. Lambda is slenderness ratio. So just remember, we have two expressions for critical load and for critical stress. So critical stress is pi square E by lambda square. Now coming back to the question. So this is a question from ISRO 2019 examination. We have two steel columns P of length L and Q of length 2L. So the name of the columns are P and Q, and the length of P is L and length of Q is 2L. Have the same cross section, strength characteristics and end condition. The ratio of buckling load of column P to that of column Q is. That is the question. So let us solve this problem. So first let us take column P. So column P, the Euler's critical load will be pi square EI by L square, because we are given that the length of the column P is L itself. And coming to column Q, the critical load is pi square EI by 2L the whole square, which is equal to pi square EI by 4L square. That is equation number 2. And we are asked about the ratio of buckling load of column P to that of column Q. So the ratio of the buckling load of column P to that of the column Q. So the answer will be pi square EI by L square divided by pi square EI by 4L square. And the answer would be 4. Okay. So everyone has got the answer right. It is option D, 4. Option D is the answer. So you can note that about the slenderness ratio and about the buckling load, the question has been asked many times. So you should know all the basics regarding slenderness ratio, buckling load, etc. and at least the effective length for the standard 4 cases. There are other cases also, you should study that for general questions. But for buckling load, we just have to apply the standard 4 cases. Okay. So far I think it is clear. Everyone can follow the concepts clearly. So moving on to the next question. Okay. So with regard to the buckling load or crippling load, both are the same. Euler's critical load is also known as Euler's buckling load or Euler's crippling load. We have another question. Please try to answer this question. The crippling load of column A is half of that of column B. If both the columns have the same height and end conditions of A and B are respectively. So the condition is that the buckling load or Euler's critical load of A is half of that of B. So what would be the right answer, right combination of A and B from these 4 options? Can you try and tell me? Please try. Which combination would be most appropriate? First end condition would be for column A, next is for B. And the value for A should be half of that of the B. So which is the best combination from these options? Aishwarya has got it right. Aishwarya, Shibina, Ayana has got it right. The answer is option D. I would explain how we arrived at this option. So correct answer is option D, which is one end fixed, other end hinged and both ends fixed. Let us see. So if one end is fixed and other end is hinged, what is the effective length? It is 0.7 L or L by root 2. So the critical load for column A would be pi square EI by L by root 2 the whole square, which is equal to 2 pi square EI by L square. That is for the value of column A. And coming to column B, we have seen the combination as both ends are fixed. So for both ends fixed, the effective length, theoretical effective length is L by 2. And substituting that, the Euler's critical load for column B would be pi square EI by L by 2 the whole square, which is 4 pi square EI by L square. So let us see. So the column B is 4 pi square EI by L square and column A is 2 pi square EI by L square, which is exactly the half of column B. So the right combination is column A is one end fixed, one end hinged, and column B is both ends are fixed. So the correct answer is option D, one end fixed, other end hinged, and both ends fixed. All of you has got the answer as right. Now coming to another topic, that is about the roof truss, that is regarding the industrial buildings. We have some codal provisions which we should know to answer such questions. So let us see. So this is also a question from ISRO 2020. The self weight of a steel roof truss in Newton per meter square may be computed by, given that the span of the truss or the span of the beam is capital M. So let us see. So the self weight of truss is given by the equation L by 3 plus 5 kilogram per meter square. So we all know that to convert the kilogram force into Newton, we should multiply by 9.81, and approximating that as 10, we get the value L by 3 plus 5 into 10 Newton per meter square, where L is the span in meter. So you should study this equation, this particular expression. The self weight of a truss is given by either L by 3 plus 5 kilogram per meter square, or you can convert it into Newton by multiplying by 10. That is L by 3 plus 5 into 10 Newton per meter square. Now let's see the options. So which would be the correct option in this case? The self weight of a roof truss. What would be the correct answer? Can you tell me? We have just seen the values. Yes, L by 3 plus 5 into 10. The value in Newton per meter square. We are asked about the value in Newton per meter square. Yes. Vaishnav, Binya, Aishwarya, Shibina has got it right. This option B. Okay. So now we will see some other questions regarding the roof truss also. In this examination, it is asked about the self weight. We should also know some other factors related to roof truss. Let us see. Now, this is another question which is about the spacing of roof truss. Earlier we saw about the self weight of the roof truss. Now it is about the economical spacing of trusses. Varies from dash to dash. Let us see. So the economical spacing of a roof truss usually varies from L by 3 to L by 5. So you should by heart these values. These are standard values which are usually asked in some of the examinations. So the economical spacing of trusses varies from L by 3 to L by 5. That is option A. Okay. Now moving on to question number 30. So this is a numerical question. So let us see the theory behind this particular question. The live load for sloping roof with slope 15 degree where access is not provided to roof is taken as. So let us see some details about this particular thing. So the angle is given as 15 degree. So if the slope of the roof is less than or equal to 10, and access is provided, then the live load or imposed load is taken as 1.5 kilonewton per meter square of the plan area. And if access is not provided, we can take the live load as 0.75 kilonewton per meter square of the plan area. So this case is about the angle of the roof truss which is less than or equal to 10. But if the angle is greater than 10 degree, angle or the slope of the roof is greater than 10 degree, then live load is calculated as 750 minus 20 into theta minus 10 Newton per meter square. Now coming back to the question, the angle is given as 15 degree. So it is definitely greater than 10 degree and we have to apply the equation which we have just seen. So to calculate the live load, we are going to use the equation live load is equal to 750 minus 20 into theta minus 10. So the theta is given as 15 degree. So 20 into 15 minus 10. So the answer is 650 Newton per meter square. And since the options are given in kilonewton per meter square, the answer will be 0.65 kilonewton per meter square. Hope it is clear for everyone. Okay. So the correct answer is 0.65 kilonewton per meter square. There is a live load for a roof having a slope greater than 10 degree, that is given as 15 degree. So hope everybody is clear about this particular topic. Yes, Binya and Vaishnav has got it right, 0.65 kilonewton per meter square. So regarding the roof truss, you should at least know the following theories. The self weight L by 3 plus 5 kilogram per meter square or L by 3 plus 5 into 10 Newton per meter square. And regarding the economical spacing, it is L by 3 to L by 5. It varies from L by 3 to L by 5. And live load can be calculated as follows. For less than or equal to 10 and greater than 10. Now coming to question number 40. A column splice is used to increase. Now what exactly is a splice? So we all know that splices are provided at the joints to strengthen them and to prevent the shear, bending moment, etc. So in a column, if splices are provided at the joints, it can be used to increase the length of the column also in cases where the length is not sufficient by the normal sections. So this is a figure which is showing a column splice or a splice which is provided in the column. So the correct answer is a column splice is used to increase the length of the column. It can be used to increase the length of the column. In a column, it can be used for that also. Yes, option A is the correct answer. Generally, splices are used at the joints to strengthen them, and in a column, we can use it for increasing the length of the column also. So this is also a question from 2020 examination. Now moving to question number 15. This is from ISRO 2019 examination. The average shear for structural steel rolled beams is calculated by dividing the shear force at the cross section by. So this is a basic logic. We are asked to find out the shear stress for a rolled section. So shear stress is equal to force divided by area. So they are asking how to divide the shear force, or to divide the shear force by what? So we have to divide the shear force by the gross sectional area of the web. So the answer is option C, the gross sectional area of the web. Okay. It is option C. This is just the basics. How to find the shear stress? It is force divided by area. So the shear force divided by the gross sectional area of web. Okay. Web are usually the part of the beam which is known as the web is usually taking the shear, and flange is used to resist the bending moment. So if we have to calculate the shear stress, we should calculate the shear force divided by the sectional area of the web, because web is used to resist the shear and flange is used to resist the bending moment. Okay, I hope it is clear to everyone. It is not the cross sectional area of the beam, it is the sectional area of the web. Okay. Now coming to the topic plastic analysis. So here also we have to learn some basic concepts and the anticipated questions regarding this particular one. So in the plastic analysis, the ratio of plastic moment MP to the yield moment My is called dash. That is the question. So most of you have got it right. It is option B, shape factor. Now let us see what is shape factor. So the shape factor of a particular section is the ratio of plastic moment by yield moment. So before going on to the details, we should know what is the plastic moment and what is an yield moment. So basically we have three types of moments when it comes to plastic analysis. The first one is safe moment. The safe moment is calculated as permissible stress into elastic section modulus, and next is the yield moment. So yield moment means the moment at which, or the moment that will just produce the yield stress, the moment at which yield stress was introduced in the section, and that is calculated by yield stress into elastic section modulus. So when the moment was safe, or when the section was safe, the moment developed was safe moment. So there you have permissible stress into elastic section modulus. But when yield stress was introduced in the section, we have the yield moment, and that is yield stress into elastic section modulus. And similarly, when all the fibers have reached the yield stress, or you can say that all the fibers have yielded, then we have the plastic moment, which is yield stress into plastic section modulus. So ZE is elastic section modulus and ZP is plastic section modulus. So these are the three moments we should know before going through plastic analysis questions. So we have safe moment, yield moment and plastic moment. Now coming back to the question, we were asked about the shape factor, which is the ratio of plastic moment by yield moment. So substituting the equations for plastic moment and yield moment. Plastic moment is yield stress into plastic section modulus and yield moment is yield stress into elastic section modulus. And the yield stress is cancelled and therefore we get plastic section modulus by elastic section modulus. Now what exactly is shape factor? Why? What is the significance? Why we are using it? Now let us see. So these are the values of some of the shape factor of common sections. And what does these values signify? Let us see. So in this table it is given that the shape factor for an I section is 1.12, which means that there is 12% reserve strength for this particular section. And now what is reserve strength? It is the additional strength a material can exhibit after the elastic region. We all know that the feature of an elastic region is that when the load is removed, the material comes back to its original shape. So after the elastic region, the yielding happens, the strain hardening happens, so and so happens. So up to which load or the additional strength a particular section can exhibit beyond the elastic region, that is known as reserve strength. So for an I section, the reserve strength is 12% or the shape factor is 1.12. Now what about a thin circular solid ray? It is 1.27. So what is the shape factor or what is the reserve strength? It is 27% additional strength is exhibited by this particular section. And coming to circular section, 1.7 or 1.69. That means 69% or 70% reserve strength is exhibited. So we should know the values of these standard sections so that we can answer the questions regarding the shape factor. So what is shape factor can be asked. Similarly, we have seen one question, or the particular value of a section can be asked, or you can be asked to arrange the different sections according to the shape factor. That has also been appeared in different examinations. Now coming to square, rectangle or an edge section, the value is 1.5. Rectangle, the shape factor of a rectangle section is a previous question also. Now coming to rhombus, the shape factor is 2. So that means 100% reserve strength is possible. So we should study all these values. It's very important. For a nice section it is 1.12, and for a thin circular ring it is 1.27. For rectangle, square and edge section it is 1.5, and for a solid circular section it is 1.7 or 1.69, and for rhombus it is 2. And we have some other sections also. For a triangle with vertex upward, it is 2.34, and if the vertex is horizontal, the shape factor is 2. So if nothing is mentioned in the question, you can go for triangle with vertex upward and the value will be 2.34. So for vertex upward, the value is 2.34, and vertex horizontal, the value is 2. Now coming to T section, it is also having a high shape factor, that is 1.9 to 1.95, 90 to 95% reserve strength. And for thin hollow rhombus, the shape factor is 1.5. So coming back to the question, it is asked, in the plastic analysis, the ratio of plastic moment to yield moment, that is plastic moment by yield moment, the ratio is called what? That is the question. The ratio is called as shape factor. This is a very easy concept, you can study that, and it is very easy to score marks from this topic because this is a closed topic. You will be asked only the standard values and the standard definition. Okay, so the answer is option B. Many of you have gotten it right. Okay. Now moving on to the next question. So again a question from shape factor. So this was asked in 2014. As I have already mentioned, you will be asked the values of different section. So the shape factor of a rectangular section is, yes, everybody has got it right. The answer is 1.5. So option B, 1.5. Yes, very good. Rectangular section is commonly asked in many of the examination, but we can expect other sections also. So we will be seeing a similar question next. Now question number 18. I will read out the question. The 4 cross sections shown below are required to be ordered in the increasing order of their respective shape factors. Which of the following order is correct? Can you try this one? You have to arrange this in the increasing order. So in order to arrange this in the increasing order, we should know the values of each and every section that is given. So try this. How will you arrange this in the increasing order according to the shape factor values? Everyone please try and post your answers in the chat box. Let us see. Binya and Vaishnav has got it right. Shibana, try again. We are asked about the increasing order. Aishwarya has also got it right. Okay, first of all, let us write down the particular values concerning these sections. So for a circular section, we know that the shape factor is 1.7 or 1.69. And for a rhombus, the value is 2. And for an eye section, the value is 1.12. And for a rectangle, it is 1.5. So these are the values. Now let us arrange it in the increasing order. So rectangle comes first, that is section 4, and eye section comes first. So, first is I section, that is 3. Next comes the rectangular section, that is 4, and the next comes the circular section, and the last one is rhombus. So, the correct answer is option C, that is 3, 4, 1 and 2. Yes, that is the correct answer, 3, 4, 1 and 2. That is the increasing order of shape factor. So, such questions can also be asked. So, to answer such questions, we should first know the values of different sections, the shape factor values of different sections. Hope it is clear to everyone. Okay, let us move on. Now, moving on to another question. This is also regarding plastic analysis. If Q is the load factor, S is the shape factor, and F is the factor of safety in elastic design, which of the following is the correct expression? So, we have already seen what is a shape factor. So, what was the shape factor? It is a ratio of plastic moment by yield moment. But load factor is the ratio of plastic moment by safe moment. So, we have already seen the expression. Plastic moment is yield stress into plastic section modulus. Safe moment is permissible stress into elastic section modulus. So, we know that plastic section modulus by elastic section modulus is known as shape factor, and yield stress by permissible stress is known as factor of safety of a ductile material. Yield stress by permissible stress. So, the load factor is equal to factor of safety into shape factor. So, coming back to the question, the correct expression is option D, that is load factor is equal to shape factor into factor of safety. Okay, the answer is already highlighted and it is clear. Option D is the correct answer. Okay. Now, moving on to question number 20. So, here we have a numerical question. Let us see. The plastic modulus of a section S, plastic modulus is ZP, is 4.8 into 10 raised to minus 4 meter cube. Shape factor is given as 1.2. The plastic moment capacity, that means MP. Plastic moment, we have seen 3 moments: safe moment, yield moment and plastic moment. So, plastic moment capacity means nothing else, it is the plastic moment of the section is 120 kilonewton meter. The yield stress of the material is. Can you try and find the answer? How to solve this problem? Plastic section modulus is given, plastic moment capacity is given, and you are asked to find out the yield stress. What would be the answer? Just try it out. Yes, Aisha has got it right. Option C is the answer. Anybody else? Yes, Binya has also got it right. Okay. Now, let us see how to solve this particular question. So, we know that plastic moment is equal to yield stress into plastic section modulus. We are asked to find out the yield stress. So, yield stress is equal to plastic moment by plastic section modulus, that is 120 kilonewton meter, that is 10 raised to 3 Newton meter, divided by the plastic section modulus is given as 4.8 into 10 raised to minus 4 meter cube. Okay. So we get the answer as 250 into 10 raised to 6 Newton per meter square, which is 250 megapascal. Yes, Shibana Aishwarya has got it right, and Binya also. So the correct answer is option C, 250 megapascal. Okay, so is that clear for everyone? These are some questions regarding the plastic analysis, and I hope that it is clear to all of you. Okay. So I think we can move on to the next question. Is that okay for everyone? Okay. Now moving on to question number 21. So this is regarding the collapse load values in plastic analysis. So first of all, what is collapse load? Let us see. So collapse load means the particular load at which a failure mechanism is developed in the section and a number of plastic hinges are seen, and that load is known as collapse load. So when we reach the collapse load, that means all the fibers have yielded, they have deformed, and it will not be able to take any further load. So that is very close to failure. So we will be asked to write the values of collapse load for standard beams. So I will be discussing the standard values of collapse load for some of the beams. So let us see what are the standard values. For a simply supported beam with point load at the center, the collapse load is taken as 4 MP by L. MP is the plastic moment, L is the span of the beam. And for the same simply supported beam which is carrying an UDL, the collapse load is 8 MP by L. It is easy to learn because for point load it is 4 MP by L, and for UDL it is a double, that is 8 MP by L. Now moving on to propped cantilever. So for a propped cantilever with the point load at the center, the collapse load is taken as 6 MP by L. And for UDL it is almost the double, that is 11.656 MP by L. So you can remember it like that. What is the value of point load? Exactly the double value will be for that UDL. So for simply supported beam it was 4 MP by L and 8 MP by L, and for propped cantilever it is 6 MP by L and 11.656 MP by L. Now let us see about the fixed beam also. So regarding the fixed beam, for a point load at the center, the value is 8 MP by L, and for UDL it is 16 MP by L. The same rule has been followed here also. So you can remember it like that, exactly the double. So for simply supported 4 and 8, for propped cantilever 6 and 11.656. That is because when you convert the UDL into point load for a propped cantilever, it is not exactly acting at the center or symmetrically, it is acting at 0.586 from the propped end and 0.414 from the other end, from the 0.586 from the fixed end and 0.414 from the propped end. So that is why we are getting a decimal value, that is 11.656. So these are the standard values for collapse load in beams. Now let us see the question. For a fixed end beam of length L and central point load of W, what will be the value of W at collapse? That is the collapse load. So we have a fixed beam which is carrying a point load at the center. So what would be the answer? Fixed beam with point load at the center. So what would be the answer for this question? Yes, the correct answer is option B, 8 MP by L. So for a fixed load, for a fixed beam it is 8 MP by L and 16 MP by L for point load and UDL. Simply supported it is 4 and 8, and for propped cantilever it is 11 and 6.56. for it is 6 MP by L and 11.656 MP by L. Okay, so the correct answer is option B. Question number 22. So that was all about the plastic analysis section. Now we are coming to tension members and their net area. So the question from 2018 is, the net sectional area of a tension member is equal to gross sectional area and dash plus the area of rivet holes divided by the area of rivet holes multiplied by the area of rivet holes minus the area of rivet hole. Now let us see some basics about the net area. So consider this figure, which is the chain riveting section. We have section 1, 2 holes are drilled in this particular section. The width of the member is small b and let the thickness be t. So what is the net area of this particular section? Net area is equal to width minus 2 into diameter of the hole multiplied by thickness, right? Because since we have drilled 2 holes in this particular section, we are not getting the entire area. There is a deduction in area. So basically, net area is equal to gross area minus area of holes. We have to remember, irrespective of the section, irrespective of the cross section, the basic equation is net area is equal to gross area minus area of holes. And this is the most simplest section we have taken. So here it is B minus 2 into D dash whole multiplied by thickness. The general expression is B minus N D dash into T. Now moving on to the second case. So imagine we have a staggered riveting case or staggered bolt case. So here I am choosing the section as A, B, C, D, E. This is my section. So what about the net area? So we have an expression which involves the staggered pitch also. So the equation is B minus 3D dash. We have 3 holes in this particular section. So B minus 3D dash plus B and C are staggered and the staggered pitch is S1 and the corresponding gauge is G1. So S1 square by 4G1 plus S2 square by 4G2, the whole multiplied by thickness. Okay, so respective to the number of holes and number of staggered pitch, the equations may change. So if we are choosing a section known as ABC, we are only taking ABC, then the equation would be B minus 2D dash plus S1 square by 4G1 into T, because we have only one staggered pitch there. We have chosen ABC. Clear? So that is the case of zigzag riveting or including the staggered pitch. Now coming to single angle section. So I have drawn a single angle section on the right side. So you can see a gusset plate and a single angle section has been connected. So we can connect it using rivets or bolts, or either you can weld it also. So I am using a rivet in this case. So I have connected an angle section to the gusset plate with one leg connected using a rivet or a bolt. Now what is the net area in the case of a single angle section? It is A1 plus KA2, where A1 is the area of connected leg and A2 is the area of outstanding leg. So in this figure you can see that this leg is connected and this leg is outstanding. So A1 is the area of this connected leg and A2 is the area of this outstanding leg. And how to find the constant K? K is found out by the equation 3A1 by 3A1 plus A2. This itself has been asked as theory question. What is the value of K for a single angle section? What is the value? 3A1 by 3A1 plus A2. Now, if it is a double angle section, so here we can see a figure which involves a double angle section. We have a gusset plate and double angles are placed back to back on the same side of the gusset plate. So here you have to note that if double angles are placed back to back on opposite side of the gusset plate, then it can be considered as two single angles acting individually. Then we have to apply the equation where K is equal to 3A1 by 3A1 plus A2. But here it is not acting individually, it is acting as a single section. We will be riveting this or bolting, we will be applying rivet or bolt to this section. So this is considered as a single angle section, single unit. Double angles which are placed back to back on the same side of the gusset plate. So in this case, net area is equal to A1 plus KA2, where A1 is again the area of connected leg and A2 is the area of outstanding leg. The same as the previous case. But K value is different. K is equal to 5A1 divided by 5A1 plus A2. So that is the difference. For a single angle section, the value of K is 3A1 by 3A1 plus A2, and for double angle section, it is 5A1 by 5A1 plus A2. This itself has been asked as theory questions in many examinations. So you have to study the K values very importantly. And also it is for double angles back to back on the same side. Because it is on the opposite side, it can be taken as two single angle section. So you have to apply K value as 3A1 by 3A1 plus A2. Hope that is clear. Okay, so Mubashir Mohammed has told that he had an examination today on DSS. So Mubashir, how was the examination? Was that easy? Mubashir Mohammed, how was the examination? You had an exam today on DSS. How was it? Is Mubashir there? Okay, so let's move back to the question. So the question was, the net sectional area of a tension member is equal to the gross sectional area minus the area of rivet hole. Option D is the answer. So irrespective of the section, whether it is double angles or single angles or zigzag riveting or chain riveting, whichever case it is, the basic expression is gross area minus area of rivet holes. So this question has been asked in the state PSC examinations also. This is very important. This is the basics of net area. Now let us see some numericals regarding this topic. Okay. So let us read out the question and try to solve it. Two steel plates, each 300 mm wide and 10 mm thick, are connected by single bolt. If the plates are in tension and diameter of the bolt hole is 20 mm, the net sectional area of the plate is. So let us see what is given in the question. The width is given as 300 mm, the thickness is given as 10 mm, and the diameter of the hole is 20 mm. You are asked to find the net sectional area of the plate. Can you just try and give me an answer? Everybody please try. First of all, try to identify the case and then tell me the answer. Okay, Aisha has already got the answer. It is option C. Yes, it is correct. Option C is the right answer. So, Aisha, can you tell me which case was that? Was it double angles or single angles or chain riveting or zigzag riveting? Which case is that? Shibina also got it right. The option C is the answer. Yes, Aisha told that it is chain riveting. Yes, it is correct. It is case 1, that is chain riveting. So, how to solve this problem? So the equation is net area is equal to B minus ND dash into T. So width is given as 300 and we have only one bolt hole. So 1 into 20 into 10. So the answer is 2800 mm square. So answer is option C. It's a very simple question. Okay. So let's move on to question number 24. Hope it is clear to everyone. Okay, so we have another question here, which is slightly different from the other questions. It's not a direct question. You have something to note in this particular one. Let us say, an equal angle of area A. It is mentioned we have an equal angle of total area A has been welded on one side of a gusset plate and carries tension along the axis. What is the effective area of the angle, or it is asked what is the net area? So we have to see that it is mentioned as an equal angle which has been welded. It is not riveted, it is not bolted, it is welded to one side of the gusset plate. Okay, so let us see. So the figure would be like, we have a gusset plate and an angle section which is an equal angle section is welded to one side of the gusset plate. Since it is welded, we can assume that no area is lost, right? So if we are riveting or bolting this particular leg, the hole has to be deducted. The area of the hole has to be deducted and there will be a loss in area. But since it is welded to the gusset plate, there is no loss in area, or we don't have to deduct the hole diameter. So effectively, the area of the two legs are going to be the same. And since it is an equal angle, you can assume A1 is equal to A2 is equal to A by 2. Why? Because we are not going to deduct the hole diameter. It is welded to the gusset plate. There is no reduction in area. So A1, A2 can be taken as A by 2. A is the total area of this angle section. And since it is welded, we can assume it has an equal area which is A by 2. Now coming to the equation, net area is equal to A1 plus KA2. And since it is a single angle section, we can go for K is equal to 3A1 by 3A1 plus A2. So substituting the value for A1 and A2, we get the answer as 3 by 4. And substituting the value of K back to the equation, net area is equal to A by 2 plus 3 by 4 A by 2. That is 0.875 A. So the correct answer is option C, 0.875 A. Have you got it right? Hope it is clear to everyone. We have taken A1 equal to A2 equal to A by 2 since it is an equal area and it has been welded. That is why. If it was riveted or bolted, we cannot take A1 equal to A2 equal to A by 2 because there will be a reduction in area for the connected leg. But since it is mentioned as welded, you can easily take it as A by 2 for both the legs. Is that clear to everyone? Okay, Shivan. Fine. So let us move to question number 25. So here also there is something we have to be cautious about. There is something different that is being asked in the question. So I will read out the question. an equal angle of area A, again the question is about an equal angle, has been attached to the support by means of an lug angle. That is important. It is attached to the support by means of a lug angle. Lug angles are used to reduce the shear line effect, and we have used a lug angle and it has been attached by means of a lug angle. If the allowable stress in tension is F, what is the load carrying capacity of the member? So, we are asked about the load carrying capacity, or indirectly we are asked about the tensile load. So, how to find out the load? Stress multiplied by area. So, load is equal to stress multiplied by net area. Since it is a tension member, we have to go for a net area. Now, what we have to see that is, it is mentioned lug angle. So, if lug angle is given in the question, you have to choose K is equal to 1. So, if lug angle is used, then K should be taken as 1. The K value should be substituted as 1. So, now things are very easy. If K is equal to 1, the net area becomes A1 plus KA2. And since it is an equal area angle, A1 can be taken as A by 2 and A2 can also be taken as A by 2. So, the value is A. The net area is equal to A. And we are asked to find out the load. So, load is equal to stress multiplied by area. That is F into A. Clear? So, in any question, if you see that it is attached by means of a lug angle, then you can choose K is equal to 1. And since it is an equal area angle, we are taking as A1 equal to A2 is equal to A by 2, and substituting the value, you get net area as A. But we are not asked about the net area, we are asked to find out the load carrying capacity, which is equal to stress multiplied by area. So, the answer is F into A. Is that clear to everyone? So, you should be very thorough about this concept. We have chosen K is equal to 1 since it is mentioned about a lug angle. So, whenever it is mentioned lug angles are used, just go for K is equal to 1. So, the answer is option D, 1 into F into A. Is this problem clear to everyone? Is that clear? Net area is not asked in the question. Load carrying capacity is asked in the question, which is stress into area. Is it clear? Is it clear to everyone? Okay. So, the last two questions were important. Both were different. One was welded, and so we took that area is equal to A1 equal to A2 equal to A by 2. And this question is mentioned that is the lug angle and also an equal area angle. So, since lug angle, we chose K is equal to 1. Okay. So, I am moving to the question number 26. Now, this is a repeated question as far as ISRO examination is concerned. It is about strut. So, we all know that strut is a compression member. And what kind of a compression member is that? It is an axial compression member. So, what is an axial compression member? So, imagine we have a column and it is an axial compression member, which means the load is acting along the axis or in the direction of the axis. So, it is known as an axial compression member. That means the load is acting parallel to the longitudinal axis of the member. While considering a beam, beam is not an axial member, it is a transverse member, because if we have a beam like this, imagine an RCC beam or a steel beam like this, the loads are coming in the direction perpendicular to the longitudinal axis. This is a longitudinal axis. The lengthwise axis is known as longitudinal axis, and the load will be acting perpendicular to the longitudinal axis in the case of a beam. So, that is why it is known as a transverse member. But considering a column, This is the longitudinal axis and the loads are acting along the longitudinal axis or parallel to the longitudinal axis. That is why it is known as an axial member. So, column is an axial member and beam is a transverse member. The load will be acting in the perpendicular direction of longitudinal axis. So, here the question is about the strut, which is a compression member. So, struts are the load carrying members of a frame which are subjected to dash. So, I have already said that column, strut, these are all axial members or axial compression members. So, the answer would be axial compression load. So, strut is a compression member. So, first of all, we should know that it is a compression member. Then only we can answer that it is axial compression load. It is not axial tension. It is not torsional load or transverse load. It is an axial compression load member. Okay, many of you have got it right. It is answer is option B. Now, a very similar question was asked in 2015 also. So, let us see that question also. Sorry, 2017. So, if you read this question, you can see that the same exact question was asked, but in a slightly different way. So, try to answer this question. Question is, a strut is a structural member subjected to dash. What would be the answer? I have already mentioned that a strut is an axial compression member. So, what would be the correct answer? Yes, option C. Compression in a direction parallel to the longitudinal axis. If it is acting perpendicular to the longitudinal axis, you will call it as a transverse member. But since this is an axial member, the correct answer is option C. So, you can see that for answering such a question, we should know the basics, which all are compression members, which all are tension members, we should know that. So, strut is basically a compression member and top of that it is an axial compression member. So, the load is acting parallel to the longitudinal axis. Okay. So, this was asked in 2018 and 2017. It is a repeated question. Okay. Now, let us move on to question number 28. So, this is from ISRO 2017. The junction between the flange and the web of a beam is known as. Now, let us see the parts of an I-beam section. So, coming to the parts, we know that we have a top flange, we have a bottom flange and we have a web in between. And we have already seen another question in which it was asked about the shear stress, which is shear force into the gross sectional area of the web. Because in such a beam, the top flange is known as compression flange and the bottom flange is known as tension flange. And flange is used to resist the bending moment and web is used to resist the shear. And what is a fillet? The junction between the flange and web is known as a fillet. So, this is one junction, this is another one, this is another junction. So, the junction between the flange and web is known as a fillet. Now, let me introduce you to some other terms also. Capital B is the width of the flange. Capital D is overall depth of the beam. TF is the thickness of the flange. DE is the economic depth or depth of the web. Obviously, TW is the thickness of the web. And fillet is the junction between the flange and the web. Coming back to the question. So, the answer is option C, fillet. The junction between the flange and web of a beam is known as fillet. Option C. Okay. Now, another question from 2017. rolled steel equal and unequal sections are designated as ISA followed by. So basically they are asking how to designate an angle section. So we have used the steel tables during our B.Tech examinations, and we have seen a lot of sections, angle sections, channel section, I sections, etc. inside the steel table. Now they are asking about how you are designating an angle section, on the basis of what. So let us see some of the standard designations. So this is an angle section which is designated as ISA 100 by 100 by 10, which means Indian Standard Angles 100 by 100 by 10. Now what is this 100 and what is this 10? So 100 designates the length and 10 designates the thickness. So I have given an example here for a rolled steel angle section, ISA 100 by 100 by 10, which means the length is equal to 100 mm and the thickness of the section is equal to 10 mm. So similarly, we can study other rolled sections also. So I am giving a rolled steel channel section. So what is the full form of ISLC? Can anybody tell me? What is ISLC? What is the full form of ISLC? Anyone? These are the standard sections that are given in the steel table. So what about the full form of ISLC? Anybody? Try. It is a channel section. So what is exactly ISLC? Anyone? Indian Standard Lightweight Channel Section, that is ISLC. So here I have designated a channel section as ISLC 400 at 45.7 kilogram per meter. So 400 denotes the depth of the channel section and 45.7 denotes the mass. Yes, Hashima has correctly answered Indian Standard Lightweight Channel Section. Okay. Now coming to a beam section. So I have designated as ISWB 600 at 133.7 kilogram per meter. So what is ISWB? Can anyone tell me? Indian Standard Wide Flange Beam, that is ISWB. So here also 600 denotes the depth of the section and 133.7 kilogram per meter is the mass of the section. So these are some usual designations we use for rolled steel sections. Now coming to the question, it is asked, rolled steel equal and unequal sections are designated as ISA followed by. We have seen 100 by 100 by 10 means the length by thickness. We are designating length and thickness. So the answer is option A, length and thickness of the legs. Okay, so option A is the correct answer. This was asked in 2017 ISRO examination. Okay. Now moving on to question number 30. Which of the following is the best compression member section? So this question you have to answer. Read the question and tell me which is the best compression member section. Is it a single angle section or a tubular section, a double angle section or an I section? Yes, very good. The best compression member section is a tubular section. That is considered as the most economical section for a column also. So what is exactly a tubular section? Let us see. So these are some of the tubular sections. So tubular section means a hollow section of any shape. You can see here, there are circular sections, there are square sections, there are rectangular sections, there are elliptical sections. So hollow sections of any shape is known as a tubular section. And why is it considered as the best section? Because for a tubular section, the radius of gyration will be maximum, because the perpendicular distance of longitudinal axis from the material, or the perpendicular distance of material from the longitudinal axis, will be always maximum. the material is far away from the longitudinal axis. So, the farther the material, the higher will be the radius of gyration and minimum would be the slenderness ratio. And that is why tubular sections are considered as the best compression members. Hope it is clear. Okay. So, tubular sections doesn't necessarily mean it is a circular section. It can be of any shape provided it is hollow. And the material is far away from the longitudinal axis. And so, radius of gyration will be high and slenderness ratio will be minimum. So, that is why we are considering the best compression member section, or the question can be reframed as the best section for a column, that is tubular section, because column is a compression member. So, question can be reframed like that also. So, remember. Now, moving on to question number 31. So, it is about lacing system, and we all know that lacings, battens and perforated plate are used for connecting built-up columns, to prevent the shear between the built-up columns. So, let us study some basics about the lacings and battens. So, let us see the fundamentals of lacings. So, what is exactly a lacing? It is an inclined member which is used to support the built-up columns. So, here we can see two channel sections which are placed face to face and it is joined together to form a built-up column. And we are using inclined members to join these columns so that it is not shearing. The shear can be resisted. Now, the fundamentals of the lacing member is that the angle of inclination of lacing bar with the longitudinal axis varies from 40 to 70 degree. You have to remember, this is a very important point. The angle of inclination of lacing bar with the longitudinal axis varies from 40 to 70 degree. This is the first thing you have to know about a lacing bar. Now, let us see the other provisions about this lacing bar. So, as I have already told, it is provided at an angle of 40 to 70 degree with the longitudinal axis of the member. And if it is a single lacing system, so what is seen in the figure is a single lacing system. We have lacing bars only in one direction. So, it is a single lacing system. So, for a single lacing system, the transverse shear force, that is shear force in this direction, this is known as the transverse direction. So, the transverse shear force is usually taken as 2.5% of load. This is very important because problems can be asked from this particular criteria. How to calculate the transverse shear force? It is usually 2.5% of the load. And the maximum slenderness ratio of a lacing bar should be taken as 145. Now, coming to other values, the total force acting on a lacing bar should be taken as F is equal to V by 2 sin theta, and minimum width of lacing bar is taken as 3D. This can be also asked as a numerical question, where D is the diameter of bolt. It can be a rivet also. So, 3D is the minimum width of lacing bar. And coming to the thickness of lacing bar, it is 1 by 40 into effective length of lacing bar. And also, we have to note that we already said that the maximum slenderness ratio is 145 and the effective slenderness ratio can be taken as 1.05 times the actual slenderness ratio, which means you can have a 5% increase from the actual slenderness ratio. So, these are some of the basic provisions you have to remember in order to answer both theory and numerical questions. Now, let us have a comparison with the double lacing also. So, what is the double lacing? We are providing lacing bars in both directions. So, there are some differences in the criteria regarding a double lacing bar. So, for a double lacing bar, the force in each bar is V by 4 sin theta. For a single lacing, it was V by 2 sin theta. When we have lacing bars in both directions, it is shared equally. So, V by 4 sin theta. The effective length is usually taken as 0.7 L, which means one end is fixed and the other end is hinged. And the thickness of double lacing bar is 1 by 60 into effective length of lacing bar. For single lacing, it is 1 by 40. For double lacing, it is 1 by 60. And for a batten, it is 1 by 50. So, 1 by 40 for single lacing, 1 by 60 for double lacing, and 1 by 50 for a batten. Now, coming back to the question, it is asked the thickness of a single flat lacing should not be less than. So, what is the answer for this question? Anyone? What would be the answer for this question? Yes, answer is option B, 1 by 40. 1 by 40th length between the inner end rivets. That means the effective length itself. Yes, option B is the answer. For the examination point of view, let me remind you, it is very easy to learn. For a single lacing, it is 1 by 40 into effective length. For double lacing, it is 1 by 60 into effective length. And for batten, it is 1 by 50 into length of the battens. Okay, moving on. Question number 32. So, you can solve this problem. You already know how to find the transverse shear. So, please answer. Okay, Hashima has asked what is the difference between lacing and bracings. So, lacings are just inclined members which are provided to prevent the shear between the built-up columns, as we have already seen. But bracings are lateral supports given between the beams. So, to prevent the lateral deflection, it can be diagonal bracings, it can be horizontal bracings, or it can be vertical bracings also. So, lacings means the inclined members which supports the built-up columns, but the bracings are used to support in between the beams. That is, to prevent the lateral deflection, you can use bracing supports which are diagonal, horizontal, or vertical. Is that clear, Hashima? Please reply in the chat box if it is clear. Okay, so the answer is option D. 25 kilonewton. Okay, Hashima. Fine. So, I will just explain the solution of this problem. So, we are asked to find out the transverse shear, which is 2.5% of the load, and the load is given as 1000 kilonewton. So, 1000 into 2.5 by 100, which is equal to 25 kilonewton. This is a very simple numerical. You can answer it very fastly. So, similar patterns has been asked in many examinations. So, you have to be careful about the criteria. Please remember all the criteria which was mentioned about single lacing and double lacing. Okay, so we can move on to question number 33. So, this is also a question from lacing. So, I will read out the question, try to find the answer. For connecting lacing flats to column section with 18 mm diameter bolt, the minimum width of the flat required is. We are asked about the minimum width of the lacing bar. Find out. Yes, it was very fast. Shibina got it right. Correct answer is option B. Yes. Aishwarya, Aisha also got it right. So, here we have already mentioned the width of the lacing bar is 3 times the diameter of the bolt or rivet. The diameter is directly given as 18. So, 3 into 18, which is equal to 54 mm. Yes. So, we are moving on to question number 34. You can answer this as well because this is also from the topic of lacings. angle of inclination of the lacing bar with the longitudinal axis of the column should preferably be between, yes, 40 to 70 degree, option C. Also remember that usually it is 45 degree. The range is 40 to 70 degree, but usually we provide 45 degree angle. Usually it is 45 degree. That is the most common angle you will see is 45 degree. Yes. So this is a very important question. This was asked in SSC examination, in state PSC examinations. This is very important. This angle range should be known. And the usual angle also is very important. It is 45 degree. Hi, Jason. Okay. So we are moving to question number 35. Now it is about stiffness. Regarding plate girder, what are the functions of stiffness? How many type of stiffness are there? How to identify which stiffener to be used, etc. So let us see the fundamentals about stiffness and then we will come back to the question. So this is an ice section where stiffeners are used. So already we have seen that this is the top flange, which is also known as compression flange. This is the bottom flange, which is also known as tension flange, and in between we have the web. So in this figure we can see that two type of stiffeners are provided. We have horizontal stiffeners as well as vertical stiffeners. So we should know that horizontal stiffeners are also known as longitudinal stiffeners, since it is provided parallel to the flange. So what about the vertical stiffness? It is known as transverse stiffness, since it is provided perpendicular to the flange. Clear? So we should know the alternate names also. Horizontal stiffness are known as longitudinal stiffness and vertical stiffness are known as transverse stiffness. Now what are the functions of these stiffeners in this particular section or plate girder? So vertical stiffness can be provided in two ways. You can provide it in between the supports, then it is known as intermediate vertical stiffness. You can provide it at the supports alone, then it is known as end or bearing stiffness, and both functions differently. If you are providing an end or bearing stiffness, that is vertical stiffness at the supports, it prevents crushing of the web. And if you are providing intermediate vertical stiffness like this, it will prevent the buckling of the web. And horizontal stiffness just improves the buckling strength of the web. That is a function. So generally if you are asked what is the function of a stiffener, the answer is it prevents the buckling of the web. And if you are asked in detail about the vertical stiffness, you have to say that the stiffeners which are provided at the support, that is vertical stiffness at the support, which are known as end or bearing stiffness, they prevent crushing. And intermediate vertical stiffness, they prevents the buckling of the web. Horizontal stiffness actually improves the buckling strength of the web. And here comes another question. Where to provide the horizontal stiffness? So in this figure, two horizontal stiffeners are provided. So the first horizontal stiffener should be placed at a depth of 1/5 dE from the compression flange. What is dE? We have already seen that it is the depth of the web or economic depth. So if you are providing only one horizontal stiffener, it should be at a depth of 1/5 dE from the compression flange. If there is a second horizontal stiffener, it should be provided at a depth of 1/2 dE from the compression flange. So these values are important and this concept is important. The horizontal stiffener should be always placed near to the compression flange and it should be placed at a depth of 1/5 dE. That is for the first horizontal stiffener, and for the second horizontal stiffener it should be placed at a depth of 1/2 dE from the compression flange. This is very important. Note the point. Now moving on to the question. So the question was, stiffeners are used in a plate girder. What would be the answer? Can you tell me? What is the answer? Stiffeners are used in a plate girder. What is the function? Yes, Hashima got it right. Option D, to avoid buckling of web plate. So if you are asked in general, what is the function of a stiffener? It is to avoid buckling of web plate. And this was asked in 2015. Okay, so now we know what is the function of each individual stiffener. So mainly intermediate vertical stiffeners are used to prevent the buckling of web. The support vertical stiffener will prevent the crushing, and horizontal stiffness improves the buckling strength. Okay. Now let us see some other concepts about the stiffeners. Now, how to decide which stiffener to be used? That is the next question. Now we will see some of the notations we have already seen. The thickness of the web is taken as TW. The depth of the web is taken as DE. Now, to decide which stiffener to use, you have to know the ratio of depth of the web by the thickness of the web, that is DE by TW. The depth of the web divided by the thickness of the web. So, DE by TW less than or equal to 85, then we do not require any stiffeners. You can call it as an unstiffened web. If DE by TW greater than 85, definitely stiffeners are required. But greater than 85 can be of any value. It can be 100, it can be 200, it can be 300. So we are going to detail about the values which are greater than 85. If DE by 2W is between 85 to 200, intermediate vertical stiffeners are required. If it is between 200 to 250, then both vertical stiffeners and one horizontal stiffener is required. So where is that one horizontal stiffener placed? It is at 1 by 5 DE from the compression flange. And if it is between 250 to 345, then vertical stiffeners plus 2 horizontal stiffeners are required. So we know where to place these horizontal stiffeners. It should be very near to the compression flange at 1 by 5 DE and at 1 by 2 DE. Okay. So these are the range of values which we have to choose. So if it is less than or equal to 85, no stiffeners are required. If it is greater than 85, definitely stiffeners are required. If it is between 85 to 200, only intermediate vertical stiffeners are required. If it is between 200 to 250, both vertical stiffeners, that is at supports and intermediate, and one horizontal stiffener is required. And if it is between 250 to 345, vertical stiffeners plus 2 horizontal stiffeners are required. Coming back to the question, the web plate is called unstiffened if the ratio of depth and thickness is less than. What would be the answer? Please post your answers. Yes, it is option D, 85. Okay. If it is less than 85, then we do not require any stiffness. So the answer is option D. Now, moving on to question number 37. So can you solve this problem and find out which stiffener is required? Try it out. Try this question and find out which stiffener is required. A welded steel plate girder consisting of two flange plates of 350 mm by 16 mm and a web plate of 1000 mm by 6 mm requires which stiffness? How to decide which stiffener to be used? Yes, you have to go for the DE by TW ratio. Yes, correct answer is option C, that is DE by TW equal to 1000 divided by 6 and you get 166.6. So this is between 85 to 200. So the answer is intermediate vertical stiffness. Yes. I hope this is clear to everyone. So you just have to find out the DE by TW ratio, and if it is between the range, you can decide which type of stiffener to be used. Okay, so that was the last question. So we are coming to the end of this session, and I really hope it was useful to everyone and it was clear. So far the concepts were clear to everyone. Was that okay? Was everyone clear about the 37 questions we have discussed? Is everything clear? Okay. Okay, so good to know that it was clear to everyone and it was useful. Okay, so thank you everyone for joining this session, and all the very best to all of you for the coming examination of ISRO, and the new dates will be published soon. So prepare well and perform well. All the best everyone. Thank you.